Gregor's going to do it. Let me just explain the system real quickly. We have a yellow card, green. Green means you're in time. Yeah? The yellow card will be held up when you have 5 minutes left for your presentation. Not just you, Hendrik. And when the red card goes up, how do they say it? We'll applaud you off the stage, so to speak. Yes, that's right.
Well, that's your job then.
Yeah, we'll have Q&A though.
Well, I think you get the red card now because it's 15 past 9, so it's my time now.
Your time. Thank you. Thanks.
Yeah, hello and good morning from my side as well. My name is Hendrik Neumann. I'm an SAP CRM consultant out of Frankfurt. Well, I'm a mentor, as you can see, with the colors. I run the local meetup in Frankfurt together with Christian, this guy sitting down there. And we also are the organizers of the SAP Inside Track Frankfurt. So we have just the first one this year, but next year there will be next one. So you watch the SCN space for the announcements and invitations, and we would be very happy to welcome lots of Bavarian people there. We had quite a few this year, and would be happy to see much more of you. So my topic today is fun with mazes and ABAP, but as I was preparing the slides and the presentation, it turned out that not so much ABAP. It just blew out of proportion and it's too much. So for now, just you have to, well, follow me. I'm pretty happy that I've got the first slot as well, because now you're all, well, get a coffee and you're up and you're awake. The shower probably still keeps you going, so you have to think a lot now. So let's start. But before I go into it, I want to say give you the reason why I come up with this topic, and it's this book. And it's a pretty cool one, Mazes for Programmers. I did read that this summer, and I think it was lots of fun. And so I want to share a little bit the knowledge and the I gained there. And what is a maze? A maze is sometimes called a labyrinth as well. This is one, and it looks beautiful, doesn't it? I think it's pretty cool. It's nice colored in it, but it's just really a maze. And why it's looking like that and what the colors mean, we come to that later. Some more, this time in green, and you can see here that all look different. So that's pretty nice. But what I want to talk about is how to build mazes, how to solve mazes. And when we want to build a maze, we first need something to build them from. So we need a grid. That's our first ingredient. Next one would be the cell. So the grid has several cells in it. The cells are divided by walls, and if we carve through a wall, we make a passage. So that's just a terminology we need when we want to build or solve or do whatever we want with mazes. So I was talking with Martin here that I needed a whiteboard. Where is my whiteboard, Martin? Because I want to build a maze now, and I want to do it the old school way with
This is a good time to tweet. We already have our first tweets about you, Hendrik.
So no whiteboard? Okay. Not as good. So we want to build a maze, and we want to use an algorithm for that, because we are programmers, and that's what we do, basically. We program stuff in algorithm most of the time. And the one I want to use to build a maze is called the binary tree. Can you see this grid here, by the way? Can you see that? Nice. Can I have another color, probably? I can.
Yep. There are a couple colors coming.
So everybody else who's presenting after me is going to be well prepared now. Ah, lots of colors.
You have to use all of them.
So the binary tree algorithm works like that. We randomly visit every cell in our grid, and then we decide that we carve out of one of these walls. When each cell has 4 walls, and we carve out either the north wall or the east wall. And that's basically it. So let's say we start here and want to carve out a wall. Northeast? North? So this one is gone then. I wanted to have this whiteboard now where I could erase it, you know? But just pretend that this one is gone. So we take the next step because we just walk through it and we have got the next one, north, east? East. So this one is gone. Next one here. This one is gone. Now we are here. And we have a special situation because if you want to carve out this wall here, it doesn't work out this way because it's a border. So we make a rule which says if we reach a border to the east, we just carve out the north one, this one. So, and it's the way the algorithm will go on. You might ask, what happens if we reach one of those with the north wall? It's just the same. We say, we carve out just the east. And for this one here, in the northeast corner, we do basically nothing. I stop with this one here because the whiteboard would have been really better. I specifically asked for a whiteboard. Whiteboard style. Okay. What we get when we visit all the cells and randomly choose to carve out one of the north or east walls is something like this. That's a pretty nice maze. Let's say, take a look at it, and we can see that there's some, we call it texture. The texture is the way the maze looks like there's lots of passageways which leads in this way. Can you see those? Probably when I put some color in it, it becomes more clear. You see that's what we call a texture. Going to be important later. And another feature of the binary tree algorithm is that we always will have a walking passage in the north and in the east, which is just a byproduct by the algorithm. Doesn't work other way. But otherwise, it's a pretty fast, pretty easy, and easy to implement algorithm to build a maze. Once we have a maze, we want to think about what kind of mazes are there. There are perfect mazes. The one we had just now was a perfect maze. It's one where we can visit every cell by exactly one path. It's logical and mathematical pure. So it's a good thing, what most of us would think. It's a perfect maze, but yet it is flawed. In a way like we have seen just now, one example was this texture. We've seen we've got certain ways, and every binary tree maze you build will have this texture in it. It doesn't work the other way. Remember that for later. What is a not perfect maze? That's the one we call braid. It's the opposite, and it's characterized by few, if any, dead ends at all. And it has many loops in it, for example. Now you can see, you can walk around this one here with the algorithm endlessly. So we don't have, compared to the perfect, here's a perfect maze. Once we move in and we are in dead end, we are dead end. So that's a thing we can use in our algorithm when we want to solve a maze, for example. Not so with a braid maze. We have, like I said, just multiple different paths inside one of those. We will look at the perfect mazes from now on. And we want to take a look at how to solve a perfect maze. For the small ones here, pretty easy by hand. You can see, a dead end, that's way. But we want a computer to do the work for us. What else? Because we are lazy, we just want to program it once, and there comes in famous name, Dijkstra. Pretty sure that many of you went to some computer class in college, university, or somewhere will remember this name. Who have heard of Dijkstra before? Show me your hands. Well, pretty much 2/3, I would think. So Dijkstra's algorithm, that's what we're going to use for solving a maze. What does it do? It measures the shortest distance between one cell and every other inside of our maze. Let's take this maze here and say we start up here. Distance from our starting point to our starting point in the northwest corner is, well, 0. We take the starting point and then we take a look at the visited neighboring cells. Distance to the next neighboring cell is 1. Now the neighboring cell is our actual cell. We take a look at neighboring cells we can visit from there on. So we've got those two. And this way we can fill up our whole maze and have something like this in the end, where we've got calculated the distance of every cell from the starting point in our northwest corner. Oops, too fast. For example, the shortest path then from the northwest to the southeast, just this way here, and has a distance 8. Can you see by there, over there? Or should the whiteboard? You can put it away. I don't need it anymore. Because I was promised a whiteboard. Yeah, like we said, we can find the shortest way between two passages here. Also possible just when we've got our result set here with the Dijkstra's results inside, we just walk back from one of the cells to our starting point. It doesn't have to be this corner, can also be this way, and so that's pretty straightforward and easy. But we can also use Dijkstra's algorithm to find the longest path in the maze. So that's probably a little bit more mind-breaking or something like that. I don't know. Perfect word now. Let's think about how we can do that. Again, a maze. This one is actually one of the outputs of a program I wrote, just in the console style. Thought it pretty nice, so I put it in here. So how do we find the longest path in a maze? We do it by first finding the longest path between two cells. So we just start with two cells and then find the longest path. So again, start up here, do a Dijkstra, and have the result set inside of our maze. The longest path we can find here is the one down here. So that's 9, 8. The A is then the 10. You've probably heard of those. Okay. But that might not be the longest path in that maze at all. It's just the longest path we can get from the 0 start point in the northeast corner. What we have to do then to get the longest path in the maze, it's pretty easy. We just run Dijkstra once again, but take our endpoint from the longest path we just found as our starting point. Because what we found might just be part of the longest path path in the maze. And that's how we run it. So we can use Dijkstra to get the shortest path and the longest path. In this case, the longest path starts in the corner we just found and goes all the way through this maze till we're down here. This was all black and white. We had before these pretty nice and looking and just, well, pieces of art. And that's the color in the maze. And what we do in the color in the maze is just we use the distances from Dijkstra calculates and then color it like from a starting point. In this case, just take the middle. If a distance of 0, so we take it white. And as longer the path goes from there, we just turn the color a little bit darker and get a nice coloring inside of the maze. And with this coloring of the mazes, we can see the differences between different algorithms pretty good. Like the texture, well, that's what we call the texture in a maze. The binary tree, like the one you know already, how it works. Another one pretty easy is the Sidewinder, almost the same like the binary tree, just a little bit different. Or the recursive backtracker, which we will be looking at later on because it's a pretty cool one as well. When you can see like they have all different textures, and if you calculate hundreds of mazes and put color on them, they will always look a little bit the same. The texture of the maze, which we just saw there, is result of the bias of the algorithm. So the mazes that come out there are not perfectly randomly. If you want to have perfect randomly mazes, we have to do some other, you have to use other algorithms. Other signs beside the texture might be the number of deadlocks you find or how long a passage in a maze is. So those are things you can calculate and where you can see the bias of the algorithm you use. But the bias itself is not per se a bad thing. It could be a thing you can use. Oh, morning, Tammy. Let's have a look at what I mean by that. Let's take a 2.2 grid. For a perfect maze, we would have 4 possibilities with a 2.2 grid, 4 cells. Those are the 4 possibilities. In a perfect algorithm, we would want to have the result set. All those should be possible. Binary tree can do binary. Okay. Who was following? Who's awake now and who can tell me the result? How many of those 4 possibilities can binary tree algorithm produce? Who knows the answer? One person only. Perfect. That's correct. It's just 50% of those 4 possibilities are possible with binary tree. It's pretty easy because binary tree, we said we have always a wall on the east and a passage on the east and a passage in the north. And those won't be possible with D and C. The Sidewinder algorithm, for example, is able to produce 75%. Just the D is not possible. But we don't look at that now. What we want to have, or what we need to have to get an unbiased algorithm is something more random, which will produce all the results. And what we do there is we use the concept of random walk. There are 2 algorithms, the Aldous border and the Wilson's. They use random walk concept to get an unbiased algorithm. And we will look at the Aldous border a little bit better, deeper, better. What we do there is we start at some cell and then move randomly from that cell to others. if we move to a cell which we didn't visit before, we carve a passage to that cell. And we end when we've visited all the cells. Okay. The result set would be something like this. And since that is probably a little bit fast for you this early in the morning, let's walk through it. Pick a random cell. Yeah, it's Oktoberfest time, right? I think that still the Munich guys are hangover from Oktoberfest. So we pick a random neighbor, this time east, and walk east. The cell was not visited before, so we carve out the wall and make a passageway there. Pick a random neighbor, the south, we walk there and go on. Then we walk to the east, make the passageway. Next random, perfect random, right? We walk to the north, but we have already visited that cell, so we don't carve the passage, we just hop over. And if you go on like that, at some point in time, you'll have visited all the cells. So if you're randomly walking through the maze, you get a perfect maze, which is totally random. No bias there. But the drawback, of course, is it might take a long time. You can, well, that's just 4.4, just take 100 times 100 and imagine how long it will take randomly to visit each cell. Might take a long time. But it's a perfect maze in the end. So we won't find a texture inside here, which is, you can see in this coloring, pretty good. And if you do 100 colored mazes, you will never get the same twice, unless your random function is broken. Well, with this long time that we have to wait there, or with the random walks, can either, a long time was just looked at, when taking the Wilson's algorithm, it doesn't take that long, but it needs a lot of memory. So we have some drawbacks with the concept of just using random walks. And sometimes bias is not always a bad thing. Probably you want to have a bias inside, like long walks, because a long walk could be a nice maze to walk through. So maybe add some constraints to the random walks to get there. We've got two algorithms for that as well here, the hunt and kill and the recursive backtracker. Since I showed you before a picture of the recursive backtracker, we're going to take a look at that one. Again, we start at an arbitrary location, perform a random walk, just like you've just seen it before, the algorithm, but we take into account which cells we already visited, and once we find no cell in the neighborhood which we didn't visit, we just walk back in our path. So we don't randomly walk over cells again we already visited. That's the constraint we built in here. The result is something like this. The bias is not as much, it's not like the texture is not carved in a certain way like we had before with the binary tree, but we can see there might be pretty long ways inside. Looks pretty nice. And again, I would like to show you how we do that, so that you understand the concept better than just from those few sentences. Again, we choose a point, let's say A4 down on the left. Then we use a stack. We put our cell there on the stack. Next, randomly choose a neighbor and put that one on the stack as well. Move there and say that's our current cell again. If we move on like this, we walk through the cells until at one point we visit a cell where we are just stuck. No way to get from this cell to a neighboring cell that is not already visited. So what we do then, we walk back and delete, or use the word pop, like it's a stack, get the first entry of our stack, delete that one. We can walk on from here because we see down here one neighboring cell. This one's already visited, this is visited, this is not visited. So that's our next stop here. Move on there, put this on the stack, and basically walk through this way, put all those on the stack until we have visited, let's say, until we find no other way. What we do then is backtrack again. And that's also like how we know that we finished with the algorithm, because now we walk our stack back until we are at the beginning again, and the stack is empty. And the algorithm is finished. When I read that the first time I saw that, I thought, I know that concept somehow. Who knows it as well? Depth first search. Well, I was reminded of my university days back then again, where the algorithm is finished and we get a nice maze with relatively long and twisty passages. So that's pretty cool algorithm to carve mazes that you can build in your garden for your kids afterwards. So it's pretty nice. The drawback of this algorithm, well, if your grid gets big, you need considerable amount of memory to keep track of on your stack. But otherwise, it's pretty fast. The reason for that is it visits every cell just twice in every direction. So, pretty nice. So now you've seen a lot of mazes, and you know the concept of mazes and how to do that. What I was doing on the side now is just I did some other programming, which I first wanted to share, but if I look at my time, yeah, good that I didn't do it. But I'm just using that as a hobby project to get into the 7.4 ABAP language, all those new concepts, and doing some programming there and having lots of fun doing that. I want to share all that later on GitHub, so just visit or watch SCN for the blog entry once I'm satisfied with code quality. And later on, probably just go into the JavaScript stuff and do it that way, like Denise would have done from the start. By the way, in the book, it's all in Ruby. So if you know Ruby is a pretty nice language as well. Yeah. What else is possible? You can build mazes in 3D. You can even use something like this. You can write with mazes. Can you? So that's our SetMook maze here. And to get back to SAP and all this enterprise stuff, lots of those algorithms. When I said almost university, I was remembered by one of our professors back at university. It's like all this shortest traveling salesman problems and how to set up your machines in your factory. All that stuff is related to the same problems here. So you can always use that in your work as well. Yeah, thanks a lot.
Thank you, Hendrik. Perfect timing, but we do have time for Q&A, so please.
Yeah, any questions?
Does anyone have a question? Okay. Yeah. All right, then we can start applying what Hendrik has taught us here. We'll illustrate it by working our way through a random path to the coffee and the bathrooms. Some of you will take the shortest path, some will take the longest, but we want you to do a recursive backtrack so that you're here on time at 10:05 so that we can start with the next presentation. Thank you, Hendrik.
Thanks a lot.